Suppose your goal is to detect if there is an object, such as a cat, in an image. If there is a cat, then draw a bounding box around that object. To detect if there is a cat or not, we can use a single neuron. If its value is greater than 0.5, then that object is present in the image, and if then value is less than 0.5, then that object is not present in image. Now, if there is a cat, to draw a rectangle around the object, we need the top left corner of the object. When we say top left corner, we mean the x and y coordinates of its top left position of bounding box. After this, we need the width and height of the rectangle to draw the rectangle. We can easily draw a rectangle if we have those four values. First, its top left corner coordinates, and then its width and height. But our goal was to also label the object in the image, and for this, we add 20 more values. These values are just to classify 20 different object types in the image. Now, if we train a neural network to predict these 25 values, where the first value is for whether there is an object or not, the next two are for its center x and y position, and the next two are for its width and height. The last 20 values are to classify the type of object we detected, either a person, a car, or something else. Now, there are two questions to answer. The first is how to train such a model to predict these 25 values accurately, and the second question is, what if there is more than one object in an image? How do we detect both of them? For this, we can add 5 more output neurons for the neural network. Now we can detect 2 objects in an image, but both objects should be of the same class because you can see that class probabilities are the same for both bounding boxes. So the total number of neurons to detect 2 objects in an image is 30. In the YOLO paper, it is mentioned that they only add 1 class probability for each cell regardless of how many bounding boxes they predict. But what if there are more than 2 objects in an image, and also they belong to different classes? For this, we use another technique where we divide the entire image into a 7x7 grid. Each grid is responsible for the detection of 2 objects in an image. This way, we can now detect a total of 7 into 7 into 2, or we can say 98 objects in an image. Now, with that in mind, the total output neurons to detect those objects can be given by this number, where 7x7 represents the total grids, and 30 values for 2 bounding boxes for each grid. Remember, if there is an object that is present in multiple bounding boxes, then the grid with the center of the object is responsible for the detection of that object, and other grids are not responsible for detecting that object. Now let's understand the loss function. For now, ignore the first term. The first summation sign is for each grid value, which is 7x7, with a total of 49 grids. The second summation is for 2 boxes for each grid. These are the actual and predicted coordinates values for each object in each grid. Now we know that many grids do not have any objects, so for those, we cannot have ground truth labels. To solve this problem, we added this extra switch, which is 1 when that grid has an object and its coordinates, and it turns 0 when there is no object in that specific grid. Thus, the entire loss for that specific bounding box of that specific grid turns 0. The next part is the same as the previous part, but this time for width and height. The only difference is this underroot part. To understand this, let's consider 2 bounding boxes, one with width 20 and height 30, and another with width 4 and height 6. The predicted bounding boxes for the first are with a width of 18 and height of 27, and for the second predicted bounding box is of width 2 and height 3. Now, if we calculate the loss for both bounding boxes, the total loss will be the same, but we can clearly see that the first box is almost accurate, and the second box is half the size of the ground truth box. So we want our neural network to focus more on this small box and predict it more accurately. By taking the underroot of the width and height, we can give more focus to small bounding boxes, so we can get more accurate bounding boxes for small objects also where it previously was focused on large bounding boxes. In the third and fourth lines of the loss, again we are taking the mean squared error for the confidence score for whether an object is present or not. Here, as we discussed earlier, This represents values of 1 if an object is present and 0 if no object is present. The second part is the opposite of the first one. The actual goal is to use this as a loss if there is an object, and if no object is present, then use this second part. We multiply this second part with a small value of 0.5 to give less importance to the loss of error if there is no object. This is because most of the grids are usually without objects, so this part of the equation already gets a lot of attention, and the model gets biased about no object. Now, to the last part of the loss equation. Here, the first part represents different grids, but the second part has the same class for both bounding boxes for each grid. This is for class prediction loss. The only thing left is this sign, which is the value of 5. This increases the loss for these first two equations to force the model to focus more on predicting correct bounding boxes. This was the first YOLO paper except for one thing.